At the LETF, so we have multiple test towers, and each one actually represents and is designed specifically in a manner that looks and acts just like the mobile launcher tower. So it's essentially many aspects of part of the mobile launcher towers. So we can be as similar as possible, right? We want to test like you fly as much as possible. What we do and what we've worked closely with is each of our SLS or Orion counterparts throughout our testing flow. So like for example, every morning we go through our test results for the day if we have them, and we have Boeing sitting there with us as we go through those test results. Every week when we're going through our test results for ICPSU, which is one of our upper stage umbilicals that has really been a long test program. We have SPY, which is our SLS counterparts there with us, and they have somebody resident here with us every single week. And that's because we want to make sure that we have good communication with them with regards to how we're doing, how we're performing. And as we work through issues, we want to make sure that we can talk quickly back and forth, and that's working well. What we found is that that's a pretty effective means for us to communicate. You know, certain things come up where we're not always on the same page, right? Where they want to add requirements, and we want to obviously take some of them away because, you know, in some cases, right, that adds cost and schedule to us, things like that. What I have found, and what I think we have found, is one of the best means to resolve those issues is to elevate them kind of quickly, right? If we're at an impasse, what we don't want to do is not make a decision in a timely manner, because the longer we wait to make a decision on some of these things, the cost just goes up exponentially, especially if we're talking about making design changes or changing test configurations, right? So what we have decided to do kind of jointly between SLS and us in certain cases is, you know, we get together, we try and understand what the differences are, and then we can elevate those pretty quickly to a joint decision-making body and say, you know, look, we're at an impasse. Somebody's going to be impacted by this. Somebody's going to have to make a decision, but that's okay, right? It's not like, you know, anybody's trying to pull one over on somebody. Let's reach a reasonable compromise and move forward and make a decision. And we've been able to do that successfully in a couple of different instances. And, you know, we both take an impact and have a path through the woods. And that's what I think, you know, it's about, right? Finding good conversation, good communication, understanding where each one's coming from, and then moving from there. It's very important for us to test like you fly, and so that's one of the things that we have worked very hard to be able to emulate and simulate at the LETF. When we talk about a test campaign, you know, a lot of people think, okay, you know, it's just you go out there, you hit a button, and it works really well. And really what it involves is months, in certain cases, of preparation. And so we spent a lot of time really manufacturing and preparing the umbilicals before we ever actually were able to test them, and that was a big surprise to our schedule. And then we had to also prepare the test facility to receive and to actually test this. So, you know, what does a test day look like and what does that involve is kind of like a good general question. So when we look at an umbilical like our ICPSU, which is our interim cryogenic propulsion stage umbilical. So this is umbilical, it weighs over 65,000 pounds. It has 2 large hydraulic actuators. It has, it has 4 primary different umbilicals on it that are all yank off. And so, I mean, this thing is, you know, 2 stories tall, right? It's just, this is a massive beast of an umbilical. And when you look at something like this, we will flow cryogenics through it, so both liquid hydrogen, and then we at the test facility will use liquid nitrogen to simulate liquid oxygen. And so on a given test day, this very large hammerhead umbilical will rotate back 90 degrees in a period of 3 seconds or so. And so here you have this large 65,000 pound plus arm, and I'm using approximate numbers, that'll rotate in about 90 degrees in about 3.5 seconds. And it'll yank off all of these different plates in that same time frame. And that will be while we're flowing cryogenics and things like that. On the other side, which we're pulling the plates off of, we have what's called a vehicle motion simulator. And in that simulator, we're representing a motion profile of the SLS that you would see on launch day. And so that's actually kind of moving in the 6 degrees of freedom of the SLS, so you would be kind of experiencing the wind profile. And what we'll do is we'll test that at each of the ranges that you could potentially experience a disconnect of the SLS. And then it'll actually do a launch profile, which is, we use large hydraulic actuators, and so we'll put it through actually a launch profile, and we do that at different speeds, but normally what we can do is at the fastest speed you would ever see an SLS lift off in. And because you want to do it at what would be your maximum clearance potentials. And so it'll actually lift off in what you would see in the first number of seconds of liftoff, and you do the retract, and then the whole arm moves back. And so really when you're out there watching this, it's pretty wild, because you have large metal structures all kind of moving around, and we have to coordinate all of this. And so our teams have gotten very proficient at this. And what you have is you have a team of a test conductor, a NASA test manager, you have a VMS operator, and then a number of technicians and instrumentation, because that's one of the big things, right? We're a test facility. What is our most valuable commodity? It's test data. And so we instrument all number of things on this arm, and we have to have it all working in order for us to go. We have high-speed cameras looking at everything because we want to understand how everything's working together. And so all of these things have to come together for a test. And we've gotten to where for an ICPSU we can do that every few days, but it's a pretty massive undertaking. And if you're flowing cryogenics, that's an even bigger deal. On some of these smaller arms, we could turn those around every couple of days. But you have to then take and analyze that data, make sure everything worked, you disconnect it exactly as you should, things like that. So the data is the most important thing, right? So if you had measurements that were broken, or if you weren't getting the data that you expected, which is, those were things that we found every single time. So most of these arms under fabrication and design, because of budget or schedule constraints, did not have significant qualification tests on them at a component level. So what we've ended up doing at the LETF is we're actually performing qual testing at the component level even, and so we're finding things that nobody ever expected, right? And so we're doing qual testing of the components, we're doing qual testing of individual subsystems and things like that. And so not only are we finding that, right, we're fixing that and trying to put the whole integrated system together. On each one of these arms, we're taking 80 plus nonconformances while trying to hold schedule and fixing everything at a given time. One of the biggest things that we've learned is, our original schedules didn't account for nonconformances, weather, and stuff like that. So one of the first things we did when I came in was I statistically modeled, what is an average nonconformance response time. We're an outside test facility, so we can estimate what is our impacts from weather. We're in Florida, right? Kennedy Space Center has excellent weather data and its historical archives. We can estimate what is the average impacts of weather. And so most of our work is done from high reaches, and so anything over an 18-knot wind speed, is going to shut us down from high reaches. Anything in a phase 2 lightning warning is going to shut us down. We can statistically model all of that, right, and understand what that is to our schedule impacts. And so and we can understand if it's better on first shift, second shift, third shift, and shift accordingly to that. And so that was one of the first things we kind of added to our schedules when I came on, was looking at that plus nonconformance impact, so we could understand what is our true schedule risk. And so we did all that, and it's and it's held relatively true. One of the things that we did not account for is some of that lower level qual testing and design impacts has been a little bit greater than we expected and anticipated. And so what I focused a lot of efforts on was how do we shrink that nonconformance response time? And so we now have chief engineers meeting every single morning at 8 o'clock and really trying to shrink what was initially a very long response time to nonconformances to we have plans in place almost within a day to 2 days for every single nonconformance, and really trying to shrink that time because that ends up being our critical path on every single one. One of the things that we encounter in testing quite a bit is nonconformances, which in previous operational programs we called them problem reports. And what it is the testing element that we're working on is not performing in a manner that is expected. And so what we'll do is we'll document it as a nonconformance, or an NC is what we call it. And that then, so basically one of the things that is very important is that we have documented test procedures for everything we're doing, and any work that we do, we want to make sure that we document it. So for example, if we're working on an arm and a hydraulic actuator is leaking, we would take that as a nonconformance, and then we would write the steps to fix that leak on the nonconformance. If the retract times of that arm is not within the expected ranges, right? If I need that arm to retract within 3 seconds, and it's doing it in 4, and I can't tune it within the parameters of the software, I would take a nonconformance and we would work out what is going on. Do I need a less viscous fluid? Do I need something like that? Anytime I make a modification to the system or anything like that, I would normally start that process with a nonconformance because it would be some error in the system or some issue with the system that isn't performing as expected. And so you would start that with an NC. And we would kind of go from there because it provides a clear documentation trail of why I am modifying or working on the system. And we want to make sure that we have that clearly documented. For each test, we have a set of different requirements. And so, for example, for our cryogenic requirements, it would be that we need the plate at X temperature for X number of minutes, and I don't remember the specifics, but to get to a cryo temperature, it would be, we hold that cryo temperature for 20 minutes or so, and it's the same as what you would expect. So we actually flow cryos through that QD interface, quick disconnect, for 20 minutes to get it to that temperature. Or, in some cases we'll be flowing cryos for several hours to get it down to that temperature, and we'll do that, and then we'll shut off the flow just prior to disconnect, and then we actually disconnect. And really what that represents is very similar to what you would see on a launch day, right? Which is what we'll do is we'll fuel the vehicle, right? So we'll flow through for hours while we fuel the vehicle, and we fuel the upper stage. And then similar to that, we have an intertank umbilical which acts as a vent for the boil off. And so, we have these cryo temperatures, and then we'll do kind of some recirc and things like that. And so those plates get and stay cold for, very long periods of time. So what we want to do is simulate, to the extent that we can, those same temperatures and conditions that we would see on launch day. And so we write very similar, what we call test requirement documents, to what we would see.